For thousands of years, the art of making metals stronger and tougher followed a pretty simple recipe. But then, back in 1995, one scientist asked a question that would change absolutely everything, unlocking a universe of materials we didn't even know could exist. Today, we're going to dive into the science behind these things called high-entropy alloys and see how one simple question is rewriting the entire rulebook of material science.
And this is it. This is the question. It's so simple, it feels almost obvious, right? It came from Taiwanese material scientist Jien-Wei Yeh. He asked, why can't we make an alloy like a mixed fruit juice? Why does there always have to be one main ingredient? I mean, you have to understand, this idea just flew in the face of, well, literally all of metallurgy's history. For millennia, the answer was always the same.
Just think about it for a second. Bronze. It wasn't an equal mix of copper and tin, was it? Nope. It was copper with a little bit of tin added in. Same goes for steel. It's not an equal split of iron and carbon. It's iron with just a tiny amount of carbon. And this wasn't just tradition, not just how we've always done it. This was considered a fundamental law of materials.
Yeah, the common belief, the scientific dogma, really, was crystal clear. If you got too creative, if you dared to throw too many major ingredients into the pot in large amounts, they just wouldn't play nicely together. The thinking was you'd get this brittle, totally useless mess. You'd form these weak compounds that would just shatter like glass. It was a rule so deeply ingrained that pretty much nobody even thought to question it.
But Professor Yeh, he did question it. And his whole fruit juice idea, it led to a complete rethinking of the recipe and a brand new philosophy of materials that we now call high-entropy alloys.
Okay, so here's the core difference, right here. On the one hand, you've got your traditional alloys. They always have one king element, a base metal like iron or copper that makes up the vast majority of the mix. But high-entropy alloys? Totally different. They don't have a king. There is no single base metal. Instead, they're made up of 5 or more elements, and they're all in roughly equal amounts. It's kind of like a team of superheroes, where everybody gets to be the main character.
So you might be asking, how on earth does that work? Well, to get it, we have to talk about something called entropy. And really, in simple terms, entropy is just a measure of disorder or randomness. So think of it like this. A neatly stacked deck of cards has very low entropy. A shuffled deck? That's high entropy. And believe it or not, the exact same principle applies to the atoms inside a metal. And you can really see this difference when you zoom all the way down to the atomic level. In a traditional, ordered alloy, the atoms have these nice, predictable places they're supposed to be. That's a low entropy state. But then you look at a high entropy alloy, and it's just this random jumble. With so many different kinds of elements all mixed together, the system basically gives up trying to create some perfect order. Instead, it just embraces a state of, well, high-entropy chaos.
And this leads to what Professor Yeh brilliantly called the cocktail effect. This is the paradox at the heart of it all. That extreme chemical disorder, that high entropy, it actually stabilizes the material. So instead of forming all those brittle compounds that everyone was so afraid of, this atomic cocktail just settles down. It forms a really simple, stable crystal structure. And somehow this totally chaotic mix creates a material that is surprisingly uniform, incredibly stable, and just unbelievably strong.
So what's the secret? What's going on inside this cocktail that gives it these superpowers? Well, it really boils down to 4 core effects that pop up from this whole new way of thinking. Okay, so here are the 4 core effects. We've already touched on the high entropy effect and the cocktail effect, right? The other 2 are fascinating. There's sluggish diffusion, which basically means the atoms move around super slowly, almost like they're stuck in thick honey. But the real superstar, the one we need to focus on, is severe lattice distortion. This is the key to why these things are so incredibly strong. Visually, the concept is just so clear. A traditional alloy, it's a perfect, neat little grid of atoms, all in a row. But then you look at the high-entropy alloy. You've got atoms of all different sizes, big ones, small ones, medium ones, all just crammed in there together. And what that does is it forces that perfect crystal grid to to warp and bend and distort all over the place. Okay, here's an analogy. Imagine you're trying to drag a heavy sled across a perfectly smooth frozen lake. It's pretty easy, right? It just glides. Now, imagine trying to drag that same sled over a field of bumpy, frozen hills. It's going to be way, way harder. That bumpy landscape, that's the distorted lattice at the atomic level. See, in metals, strength is all about how hard it is for tiny defects, called dislocations, to move. This bumpy atomic terrain acts like a massive obstacle course, and it pins those defects in place. That's what makes the materials so incredibly strong and hard. And look, this isn't just a neat theory. We can actually see the evidence for this in computer simulations. What you're looking at here is a chart that shows the average internal strain in 3 different high-entropy alloys. Now, as you go from the alloy on the left to the one on the right, the difference in the size of the atoms in the mix gets bigger and bigger. And just look at what happens. The atomic strain, which is basically a direct measurement of that lattice distortion, it just shoots up. So it's simple. A bigger difference in atom sizes means a bumpier atomic landscape and, you guessed it, a much stronger material.
All right, so that's the science, that's the how behind it all. But what about the what for? I mean, why does this matter? Well, this completely revolutionary approach is opening the door to applications that honestly used to be pure science fiction. Let's talk about some of the game-changing possibilities here. For aerospace and energy, you can design these alloys to have incredible strength even at blistering hot temperatures. That's perfect for building the next generation of more efficient jet engines and power turbines. Then there's biomedical stuff. Their unique combo of super strength and resistance to corrosion makes them absolutely ideal for implants like hips and knees, things you need to last a lifetime inside a human body. And of course, their sheer hardness means we can create things like drill bits and protective coatings that are practically indestructible.
Okay, so if these materials are so amazing, you're probably wondering, why isn't my car made out of them? Right? Well, the very thing that makes them so incredibly powerful also happens to be their biggest challenge. And that challenge is complexity. The number of possible recipes is just astronomical. I mean, with dozens of different elements you could potentially mix together, you end up with billions and billions of possible combinations. So how do you find the one perfect recipe for what you need? Trying to do that with traditional trial and error, it's like trying to find one specific single grain of sand on every beach on Earth. It's practically impossible. So to even try to navigate this massive space of possibilities, scientists have to rely on incredibly complex computer simulations, kind of like what you're seeing here. They use them to try and predict how a specific mix of atoms will actually behave. But this is a huge computational challenge. I mean, accurately modeling how all these different elements are going to interact with each other, it's just incredibly difficult and takes a massive amount of time and computer power. So really, when you boil it all down, the limitations come down to a few key things. First, it's just plain hard to predict their properties. Second, the development, especially with some of the more exotic metals involved, can be really expensive. And third, figuring out how to produce them economically and on a large scale is still a major challenge. And all of that together is why, for now, these alloys tend to stay in the world of high-performance, niche applications.
But that is not where this story ends. Not at all. Because that huge challenge, the complexity, is also the field's greatest promise. Because what it really means is that we have only just begun to scratch the very surface of what's actually possible.
Professor Yeh himself put it perfectly. He said the field of high-entropy alloys has opened the door to a treasure mountain. He said the old map of metallurgy, it only explored the foothills, but now we have an entire mountain range to explore. We are literally standing at the base of a treasure mountain of new materials. So how are we going to explore this vast new territory? The key, the tool that will let us climb that mountain, is artificial intelligence. By combining those powerful simulations we talked about with machine learning, researchers can sift through those billions of combinations way, way faster than any human ever could. The AI can spot patterns, it can predict properties, and it can point scientists directly towards the most promising recipes for the super materials of the future. So, just by daring to ask a really simple question, by deciding to mix a new kind of cocktail, we broke one of the oldest, most fundamental rules in all of metallurgy. We've basically thrown out the old recipe book, And now, we're faced with an almost infinite palette of new ingredients. So the only real question left is, what are we going to build with all these pieces?